right. That means, by the intermediate value theorem, that there is some point f at c which is equal to 0. Okay? That's the intermediate value theorem. All right? The three possible cases are that this number is less than 0, this number is bigger than 0, or this number is equal to 0. All right? And I don't know how many of you guys remember doing this, but maybe your teacher proved the intermediate value theorem, and there's actually 3 cases to prove that. Okay? So if you ever want to, just go in your calc textbook. The proof is literally like this long. It's a very short proof. But that's somewhere in real life mathematics that cases would be utilized. Okay, so I didn't want you guys thinking that, like, division into cases is just one of those oddball things. It's actually used quite often. Okay, so any questions about like intermediate value theorem? By the way, if you're running a computer program, the intermediate value theorem is really important, because what if there is no 0? Then it goes into an infinite loop, right? So one of the first things a computer programmer might do is just to make sure that the 0 exists. Then you can run your algorithm to try to find it. Okay, so that's where I remember utilizing the intermediate value theorem. All right, anyway, besides all this calculus crap. Okay, so the 3 types of different types of cases of integers are the main 2 I'm going to ask you guys to utilize. I'm not going to ask you guys to do positive, negative, or 0, but I'm going to ask you guys to be familiar with even and odd cases, or the form by the quotient remainder theorem. Okay, which is why I just demonstrated what we just did. Okay, so division into cases is actually very similar to the stuff that we've already been doing, except we're going to do it twice instead of just once. Okay, so if I ask you guys to prove something by division into cases, you define your variables just like we did in the previous type. Then what you guys want to do is just write out all the possible cases and then prove each case. If the original is true for all the cases, then you can say by case 1, case 2, case 3, case however many cases there are, the original statement is true. Okay? Alright, so what I want to do, guys, I want to start out with a really basic example of division into cases, okay? And then maybe give you guys like 1 or 2 to practice. Okay? This is a very typical type of problem where division of cases is used. Okay? So I want to prove the following. Okay? I want to prove that for all integers x, okay, that such that x is an integer, I want to prove that this structure right here is always odd. Okay? Now, before we even start the proof, what's the first thing we might want to do?
Define them.
Yeah, let's let x be like some sort of number, right, guys? Because what if it's not true, and we just go through and do the proof for like 20 minutes? Well, we just wasted 20 minutes of our lives, right? We don't want to just assume it works, even though in our class it's probably going to work. Okay? So let's just go ahead. You don't have to write this down, but what if x equals 0, guys? Well, don't we just get positive 3? So then the output is 3, which is certainly odd. Okay? So it works for 0. Okay? What if x were equal to 2? Let's use an odd number, but not 1. Because I think if we use 1, we get 3 out of it again. So let's say x were to be equal to 3 for some reason. Okay? If x is 3, we get 9 minus 3 plus 3, which is 9. Right, guys? So, just by using a couple basic numbers, we can obviously see that it looks like it's going to work. Okay, so that might be your first step. And I know it takes like maybe 20 seconds to do this, but it's better than wasting 20 seconds than wasting 20 minutes doing the proof. Okay, and I'm just trying to get you guys to think, when you do it in real life, this is what you guys might have to do first, is just check with trivial cases to make sure it works. Okay, so here's our proof. Okay, guys, there's only one variable. Okay, so this is important already. So let's start by saying, let's let x be an element of the integers. Okay, sounds like a good idea. And you don't have to, but you can say arbitrary but particular.
Aren't you going to write step 1, step 2 on this one?
Oh, you can if you want to, but because it's division into cases, and because we already know step 1, 2, etc., we should be okay with that.
Okay.
But you can go ahead and label it. Now, what do we usually do, guys? Don't we use some sort of definition?
Mm-hmm.
The problem is there is no definition for integers, right, guys? I mean, we know that's just a whole number, either positive or negative or 0.
We do have z odd, 2k plus 1.
Well, that's odd, and then...
So you have to use the definition for an even and an odd.
Right, so we have to show it once true for even, one's true for odd. And guys, isn't it true that every number, every integer, exhibits either even or odd pairing? Okay? If you guys think of any integer, it's got to be even or odd. Okay? So here's what we're going to do. And again, I'm going to put this in brackets. You don't have to write this. But we are going to divide into even and odd cases. Okay? All right. And guys, most of the time when you're doing integer proofs, even and odd is the easiest way to do it. Okay? So my suggestion would be, like if you're in a class, you have no idea where to start with an integer proof, start with even and odd. I mean, there's only two possibilities. Okay? So now what we're going to do is we're going to do the proof itself. Okay? So this is case 1. Okay? So case 1 is where x is in z even. Okay? So here's how we're going to start this. We're going to say, let's let x be in z even. Okay, so you have to define x to be an even variable. We've never done that. We're just saying right here that that's the case. So let's let x be an element of z even. Okay. What can we say about x then?
By definition, x is equal to 2k.
Sure. Or k is an integer.
2k is an
So, by definition of even, x is equal to 2k, or k is an integer. Okay, so that looks good to me. Just like you guys did on your homework, or just like you guys did in class, okay? What's the next thing we generally do after we define the variables? Substitute, right guys? That's exactly what we're going to do. We're going to substitute 2k back into the original statement that we're trying to prove. So by substitution, x squared minus x plus 3 is going to be equal to quantity 2k squared minus 2k plus 3. Okay, so let me get out of your guys' way, make sure that's okay. Yeah, this is a pretty easy proof. We've done this several times with integer stuff. I bet you guys probably already know what the next step is without thinking about it. So what is your nose or what's your intuition telling you to do at this point? Besides go home.
by multiplication.
Yeah, just square out the 2k, right?
Yeah.
So just square it out. I mean, that's what you guys would do like in real life. So now we're in math life, might as well do it. Because math life and real life aren't the same thing. So doesn't this become 4k squared minus 2k plus 3? And that's just by multiplication. Or exponent rules, power of a product rule. You know, I'm pretty flexible with the rules, okay? As long as you don't put like puppy dog tail or something like that. Okay. All right, what are we trying to show with 4k minus 2k plus 3? We're trying to show
It's
that
even.
it's not odd,
Odd,
right?
right.
Because remember at the beginning we said it's odd. Okay.
But we're doing this case one is for even, right?
Well, no, we let x be even.
Oh, okay.
But remember, we're trying to show that the original result is odd. Okay,
Oh.
so this one we're letting the variable be even. Does that make sense? Arthur?
Gotcha, gotcha.
Okay. So, does anyone, what's the form of
Four
odd,
kids.
by the way, guys? 2k plus 1. Okay, so we're really close, but I think that 3 is kind of throwing some of us
So
off.
2 plus 1.
Go ahead.
So you rewrite it as 2 plus 1?
Yeah, we could just rewrite 3 discretely because it's 2 plus 1, right? Nice. So just by some basic computation, and we've seen this before, right guys? We did this trick. We can rewrite this, since 3 is 2 plus 1, which I highly doubt anyone in here doubts, but if you do, let me know, because then I'll be scared for your safety. Andre, that's not a good thing. I'll give you a hug later. And guys, isn't it obvious that we can factor 2 from those first 3 terms, right? And then we can just use closure and we're done, right? This, I mean, it's just so obvious, okay? So we're going to factor it 2. I'm going to write the steps in at the end, by the way. Okay, so 2, when we factor 2 from the first 3 terms, 2k squared minus k plus 1 end quantity plus 1. And then finally, guys, couldn't we say something about 2k squared minus k plus 1? We can make that equal to p, m, whatever letter you want, as long as we haven't reused it. So this is going to be equal to 2p plus 1, where p is an integer. Alright. If I were to fill in the steps, okay, the one after multiplication, that's just computation, okay?
Would we have to write that computation?
Did you write something different?
No, I didn't write anything yet.
Yeah, you have to justify the step, okay, because it is a proof. Guys,
Computation's pretty broad, right? You're saying that that's just like a general.
when I say computation, computation's like number operations, okay? So it's basically like if you're, whenever you hear the word compute, that means you're simplifying an arithmetic statement, or making it more complex if you would.
So could I write computation for the multiplication?
It's more algebraic, but yeah, sure, if you wanted to write it, that's fine, alright? So, this guy right here is GCF. And then this guy right here is closure. Okay.
GCF applies with two variables, there's only one variable, right?
Wouldn't that be factoring QCM?
Well, we factored out the greatest common factor. So if you wanted to write factoring, but you really are, yeah, we have two different, well, it's the same variable,
Uh-huh.
but since they're not like terms, there still is a common factor between those, okay? If you just want to write factoring, that's fine too. Okay. Alright, so guys, any questions about this one, guys? Okay.
Can you like skip the one computation step and just go straight to the GCF?
Yeah, that's fine with me, okay? I just want to make sure when people go home, it's like, oh, how did that all of a sudden become that? Okay, saves me a little bit of headache. Alright, other questions, guys? Alright, so, good news is we proved case 1. Bad news is we haven't yet proved case 2. That's what we're going to do next, okay?
So do we have to write on the end of this by blah?
Nope, because we're going to do that at the very end to save ourselves a lot. That's alright, that's a good question, okay? I'm trying to make this as efficient as possible. We'll say that, which is just a nice word for lazy. Alright, so now we're going to do case 2. And this time, case 2 is where x is an odd integer. Okay. We're going to do the exact same thing, except now we're going to define x to be 2k plus 1. Okay? So, we're going to say, let's let x be an element of z odd. Okay. By definition of odd. X is equal to 2k plus 1. Okay? Where k is an integer. And guys, the steps are going to be almost identical. It's just going to be a little bit of algebra difference in there. Okay? So what was the next thing that we did after we defined x to be even in the previous proof? Substitution, right? So by substitution, yeah. So by substitution, we're going to say that x squared minus x plus 3 is now going to be equal to the quantity of 2k plus 1 squared minus the quantity of 2k plus 1 plus 3. Okay? And notice, guys, every time I substitute everything, I utilize a parenthesis, especially if there's more than one term. Okay? It wouldn't be completely wrong, okay, if you guys, you'd still get the right answer. It would still be mathematically wrong if you forgot the parenthesis around the second step, okay, because there's a negative that has to get distributed there. All right. So, at this point, guys, what do you think the next step might be to be able to prove that this thing's odd?
Multiplication.
Yeah, FOIL everything out, right, guys? We have a lot of stuff to distribute, okay? So, by multiplication, now be careful, this guy right here, that's not 4k squared plus 1, right? Okay? What does this animal expand into?
4k squared plus 4x plus 1.
4k squared plus 4k plus 1, right, guys? That's okay.
Yeah.
That's all right, no big deal. I bet you wrote k.
Yeah, I wrote it.
That's okay. No big deal. You were just thinking of the expanded binomial, okay? What if you don't remember that, okay? What's the easiest way to remember, like, how to get to that thing? Like, just in case you don't remember, that's the proper expansion.
Write it out twice.
Yeah, if you guys don't see that, what you guys do is you just write it as 2k plus 1 times 2k plus 1, and then you just do your FOIL, 4k squared plus 2k plus 2k plus 1, and then clearly that's 4k squared plus 4k plus 1, okay? So remember guys, if you're not good with your basic algebra like that, you can always beat it up by just doing the basic expansion of that.
What about Pascal's triangle?
What's that? Or you could use Pascal's triangle if you're good with that. So I'll never ask you to do a cubic though, so don't worry about that, or a quartic. We're going to distribute the negative, so that's minus 2k minus 1 plus 4k. Okay? So it's just by multiplication. Notice if you forgot the parentheses, you would get minus 2k plus 1. You'd still get the right answer, but it would mathematically be incorrect. Okay? What seems almost like it's beating you in the face for the next step? Yeah, like terms. All right. I mean, if we don't know that, then oh boy, that's bad. But you guys know that. So by combining like terms, I believe 4k squared plus 2k plus 3, right guys? Just regular old polynomial goodness. Guys, doesn't it look almost identical to the previous, except instead of a minus 2k, we have a plus 2k. We can use the exact same trick where 3 is 2 plus 1. Okay, so we're almost done with this animal. So this is going to be equal to 4k squared plus 2k plus 2 plus 1. Okay, again, that's just by computation. We can factor out the 2, okay, so just by GCF, twice the quantity of 2k squared plus k plus 1, n quantity plus 1. Right. And just to make it really easy on ourselves, I'm going to reuse the same variable. Okay, so instead of 2k squared plus k plus 1, I'm going to say by closure that's p. Okay, so just by closure,